right. Okay, so there's some things in 10.3 that we didn't get to do, like higher order derivatives, Laplace's equation, and the wave equation. You're expected to teach yourself that information. Okay, there's quite a bit of homework in that section, and it's a very important section, so take that seriously. I will be moving on to 11.4. Concept of tangent planes. Okay, so this is where calculus is getting really astonishingly cool. It's constantly getting cooler and cooler. So let's do a recap of the calculus we've done before real quick. Before we had a curve. We wanted to know what is the slope of the tangent line to some point right here. Where we say, like, you know, this tangent line is equal to some mx plus b. We want to know what is this m. We realize that if this is some function f of x, this is at some point a, then that m is equivalent to f prime of evaluated at a, right? That's what we realized. So in Calc 3, now our curve becomes like a plane, if you will. Then, on top of that, we can have some type of like curve defined that resides on that plane. Next, we can say, okay, at some point P, what is boom? What is the slope of this tangent line in the x direction? And what is the slope, boom, of this tangent line in the y direction? Okay, so maybe call this Tx, Ty, where this point right here, bring it down in its projections. This is at some A, some B, and it has a Z component, C. So this point right here, we'll call this point P, A, C. We realize that not necessarily the line, but the slope of the tangent line would be this. And the slope of the tangent line here is going to be this. Now, oh my goodness, we have a full house. That's good. We have a full house today. Okay, this is very good. So now, we had a tangent line here. We want to construct a tangent plane. What is a tangent plane? A tangent plane is the plane that contains these lines, the tangent lines. Boom. Okay. So the tangent plane contains the tangent lines Tx and Ty. And it's not necessarily the same as our surface f of xy, right? Here in the white, this is our surface f of x, y, which can be thought of as a z. It's not the same as that, you know? It's different. And at every point, we can define a tangent plane. It is the plane that contains the two tangent lines, okay? So, how do we go about defining such a thing? Well, what you realize is when you apply the plane definition that we already utilized, and you solve for some constants, and you set some values equal to another constant, you're able to derive this equation. I believe this is going to be x minus x, if I remember correctly. Yeah. So here goes our beautiful, colorful picture. Now we understand what's going on. So would you take a look at this here? This is a very beautiful equation. So really, it looks like a y equals mx plus b, but twice. So we don't have a y anymore, we have a z, okay? This can be thought of as your analogous to your y-intercept. It's no longer so, it's like your z-intercept. And now you have two slopes. You have an mx, you have an my. Before you had y equals mx plus b, but now you have such an equation right here. These are just analogies that I'm drawing towards lines, okay? It's a very appropriate analogy. It's not just some figment of the imagination here. When we add another dimension, what we're doing is our equation becomes this equation. And you guys know that this x naught, y naught, z naught comes from our p naught. And our p are different points on our planes. Our p naught is the original point on the plane. So after this theoretical development, let's do a concrete example. How about z is equal to 2x squared plus y squared? This is equal to our function. Okay. So let us find the tangent plane here at the point 1, 1, 3. So clearly, we're going to have to take some partial derivatives with respect to x and with respect to y. Okay, this reduces to, because it perceives that y squared as just a constant, so this just becomes 4x. Now let's take the partial derivative with respect to the variable y. So then this becomes 0. Okay. So our fx and fy give us these values. So we'll be plugging that here and that here. Then we just need to know what is my x naught, y naught, z naught. Here they are. So this equation becomes z minus 3 is equal to this guy evaluated at x naught, y naught. So that means this thing evaluated at x naught, y naught is equal to 4 times a 1, which is a 4. This goes here. X minus my x naught, which is 1, plus, what is my f of y? F of y, 1, 1, is my 2 times the 1, which is 2. So we get that is equal to 2 times y minus y naught. Okay? And then let's just distribute this 4x minus 4 plus 2y minus 2. Let's regroup some terms. This becomes 4x plus 2y minus 6. Add a 3. I get z is equal to 4x plus 2y. Add a 3, so this becomes minus a 3.
Do we have to go that far, or can we just leave it?
That's a great question. If we want our expression to be for a surface, typically a surface in R3 is some function of two variables, f of x, y is equal to z. So if you just left it like this, it's not in this standard form. So we want to know what z equals, because z is like the output of a two-dimensional input for x and y. So I get various x and y, I plug them in, and it spits out something. Yeah. So yes, we kind of do. We kind of have to, yes. So there you go. This is the equation for the tangent plane of this surface. Who could tell me what this surface is? It's a what? A cylinder? Oh, it's close. It's kind of hard, to look at an equation and be like, oh, I know what that is, unless it's like a circle or something, or a sphere. This is an elliptic paraboloid.
Yeah.
You're gonna guess a cone?
I guess one of those.
Right. So here's how you do it. Let's flip back. I'm gonna show you. I'm gonna empower you guys with how you would be able to tell, for sure, no matter what. Let's go back to the section where. Which section was it where it characterized all the different kinds of surfaces and gave us the equations for it? 9.6. Thank you, Jamie. The standard equation for an elliptic paraboloid is z over some constant a is equal to x squared over a squared plus, this should say c. This should say c. And this is a y squared over b squared. Okay. So how does that look like that? Well, we can divide both sides of the equation by 2. And I get z over 2 is equal to x squared all over 1 squared plus y squared all over 2. Okay. But what is 2 is really what squared?
Square root.
Yes. Right. And this 2 doesn't have to turn into anything because the standard form doesn't have any squares there. So that's how you can see, oh, it's an elliptic paraboloid. So the way I would do it is know the standard forms, get your equation to one of the standard forms, and then you'll realize which one it is. Because it can only turn into one of them, right? These standard form equations are such that mathematicians have discovered that they only turn out to be equaling this kind of standard form. Somebody guessed a cylinder. let me see here. Recall that like a cylinder would be this. Like a cylinder would be some x squared plus some y squared equaling some value c. Where you say like z, where you don't specify z is free. Then this would then create like a cylinder about the z-axis of radius c. Okay. Yeah, these are all very important things. Although we've moved on from those sections, they will pop up. So feel free to constantly refresh yourself throughout this course. Because as you guys know, mathematics is a interconnected subject. It's very interconnected. And yeah. See, now we're referencing planes. That was from test 1. So you're expected to not like dump that information out of your brain, even though it can happen. It can happen. It's not unheard of, but just make sure as it dumps out, you pour it back in. Right? That's how I think about it. Moving on to linear approximations. Okay. You guys remember linear approximations in Calc 1? Or was that Calc 2? I'm not sure. I think it was Calc 1. That's okay. So here's the theory behind it. Let's say you have some arbitrary curve. Okay. All right. Well, that curve is really hard to like model, you know. I try and model it with polynomials and it doesn't really work out. How can I create a model for this curve? Well, mathematicians state that, okay, let's zoom in on some interval of the curve. Notice that it can be approximated with a straight line. So at any point on the curve, even this really curvy spot right here, if I take my interval short enough, it can be approximated with just a straight line. If I take it short enough. So that's the whole concept behind a linear approximation. It's very powerful. But now we're moving on to Calc 3. So what we want to do is create linear approximations to two-dimensional surfaces in R3. Okay. So let's talk about the tangent plane we came up with earlier. Did I erase the value? I did. So let's keep this like this. The tangent plane we came up with earlier was z is equal to like -3 plus 4x plus 2y. Thank you, sir. 4x plus 2y. All right, and our point of interest was this 1, 1, 3, I believe. Okay, so we're on the same page. Now that we've created a tangent plane to the surface that was given to us, let's create a linearization of our function at that point, okay? And the original function was 2x squared plus y squared. Okay, and then what we can derive here is that this term is actually some f of 1, 1, is it not? Check. f of 1, 1 is equal to 2 times 1 squared plus 1 squared. That's 2 plus 1, which is 3. Oh, but that's 3. This is minus 3. Remember, it was over here on this side. Remember, we had z minus z naught. So it was that 3 popped up over here, and we subtracted it from both sides to get it to come over here. So that's why it has a minus sign on it. Okay. Then we noticed that this term 4, it came from where? Did it not? And we noticed that this term here came from this. Did it not? It did. So our linearization is really just the same thing, okay? It's the same thing as this equation for the tangent plane, okay? In general, a linearization, a surface linearization. Before we talked about a curve and a line that linearized the curve. Here, we're talking about a surface that would planarize a weird undulating surface. So you have a really nice sheet. Okay, that's beautiful. And then you have this weird undulating surface. It's beautiful, but it's very chaotic. We want to be able to systematically determine its values. We say, okay, at every undulating weird point on this surface, this two-dimensional surface, we say, okay, at every point I can create a tangent plane. And the plane behaves really well, just like the line behaved really well, compared to the weird squiggly curve. So your book defines it like this. Boom, bada boom, bada bing. Where are these A's, B's, and C's coming from? Okay, they're just your point of reference. Before it was X naught, Y naught, Z naught, which was 1, 2, 1, 1, 3. And now it's just A, B, and C. Potato, potato, tomato, tomato, it doesn't matter. Okay. So, now let's talk about what it means for a function to be differentiable at a point. Because we already talked about what it meant for a function to be continuous. The gist of this stuff is that the tangent plane is the two-dimensional linearization. If that makes sense. The gist of all this stuff is that the tangent plane we constructed is now a two-dimensional linearization. So let's given some function z is equal to my f of xy. We say that f of xy is differentiable if it needs to be differentiable at if its derivative should exist. Okay. So its derivative really is a change in z. Okay, if our function is equal to a z, then the rate of change of that function z is like a delta or a difference. So if z over there is equal to a f of xy, we can quantify changes in this function in two directions, a delta z delta x, a delta z delta y, right? So changes in z are truly changes in the function's output. And quite simply here, we think of an analogous situation to a line. Plus these terms. Okay. So don't worry about that epsilon 1, epsilon 2 thing, all right? Those are just consequences of the derivation. Really, this delta z comes from the definition of an increment. Final minus initial, okay? Final. Oh, that should be x. Sure. And clearly, I put x and I put y here, x and y, x and y. But clearly, we can evaluate the function at a concrete, specific point, right? So at a specific concrete point, AB, let's say we're evaluating the function at AB, then this expression becomes this. And by that, what do I mean? I mean that my f of my surface z at AB, that is given by these points. I want to say this is equal to z. I'd say that this is equal to the surface. Because you got a point A, you got a point B for x and y. And then to determine z, you use it in the equation. So this increment definition over here is just an application of a change in some value in z. We notice that a change in some arbitrary value of z given some delta x and some delta y can also be expressed as this. Why? Because this fx and fy basically determine the slope of a line going along the curve in the x and a line going along the curve in the y. This epsilon 1 and epsilon 2 business, you need not worry because epsilon 1 and epsilon 2 approach 0 as what? We take smaller and smaller subintervals. So in the limit, as the subintervals or the changes become small, so this just reduces to this in that case. And if delta x and delta y are getting really small, this is how we can define a differential. So these go to 0. So this is the definition of a differential. This is very, very cool. This is a differential. A differential in math is like the smallest quantifiable entity we can think of. So it is the smallest quantifiable change in the function. Its z value can be given by these. So, okay, what do I mean by that? Okay, let's say that this whole thing is of length x. All right. This tiniest amount right here is what we would call dx. The smallest piece of x. And then if you even got dx, if you somehow could blow that up and call this whole thing the dx, this would be another dx, right? But we are assuming that this is not possible. That dx is just so tiny, even if you zoom in, it remains tiny. Okay. So that's the definition of differentiable. That's the definition of a differential. And another way to define something being differentiable is a theorem in the book. Here's the differentiability theorem. It says, okay, that weird definition right there, we don't necessarily have to satisfy that. All we got to satisfy is at some point AB, given some at some point AB, given some function f of x, y, don't forget is equal to z. If f of x, a, b, if f of x, y, and f of y of x, y exist, and not only do they have to exist, but they have to exist near AB, and they're continuous on AB. Recall that that implies that this and this exists. We say that the function f is differentiable at AB at that point. So all you need to do is to determine, is this function differentiable? Okay, take partial derivatives with respect to x and with respect to y. See whether, when we plug them in at that point, if those values exist, and if it's that would imply it's continuous. So okay, here's an example. See here. How do I want to go about explaining this? Okay, how about our original function here? Let's see if it's differentiable. The function we've been talking about this whole time here. Let's see if it's differentiable. What was it? It was f of x, y. Recall we found the partial derivatives. Okay, so is this differentiable at 1, 1, 3? So we plug the values in. So it exists, and we plug the values in. So it exists, meaning it's continuous at this point. So at some point AB, given the function f of xy is equal to z, the partial derivatives existed because when we took the derivatives, it outputted some value that made sense. And it's continuous at AB, which is like 1, 1 in this case. So that means it's differentiable at AB. That's just an example. So on your homework, quiz, or test, I may give you a function, and I will say, is this function differentiable and why? So you would say, based off of like the differentiability theorem, all we have to show is that the function has partial derivatives that exist and that we can evaluate at the point of interest, showing that they're continuous. That means it's differentiable at that point. It may not be differentiable across the whole surface, but at that point that we're talking about, it is differentiable. Let's see here. So we've talked about two different ideas here. We've talked about linearization, and we've talked about differentiability. So let's apply this concept to a different function than just this function 2x squared plus y squared. Let's do another function. We're getting bored of this guy. Let's say x e to the x y. Let's say this is our function. And let's say our point of interest is 1, 0. Okay. Is it differentiable? That's our first question. Here's question number 1. Let's ask the question and answer the question. Well, you already know what time it is. It's time to take some partial derivatives, right? Yeah. So notice that this is a product of two functions in x. So what do we have to do? You have to say that this is equal to this. What rule is this? Yeah, particle. So derivative of x is just 1. And then that e to the xy just comes along for the ride. Over here, now we're going to address that e to the xy. Well, e to the anything is just itself, but then we have to do the what? The chain rule. Yep, the chain rule. And when we do the chain rule, now partial x of xy becomes just y, right? So then this becomes y times x times e to the xy. Ugh. It's really nasty when you have like a hair in your mouth inside of a mask. Yeah. Ah, there we go. I got it out though. Here we go. Now some f of what's this guy of our function. So partial y just ignores that x. It just thinks it's like a. It ignores the x. It just thinks it's like a number or something, right? So boom. Now it can't ignore the e to the xy because there's a y in that situation. So then what happens here is this becomes, and we must chain rule. So this becomes x times e to the xy times partial y of xy, which gives me what, guys? It becomes just x, right? Very good. Right? We're just taking partial derivatives. So, but that's not it. So the part of the theorem said, okay, our function is differentiable at that point if the partial derivatives exist, and when we evaluate the partial derivatives at that point, the function is continuous, meaning it evaluates to a value that makes sense, meaning it's not undefined. So when I plug in a 1 for x and a 0 for y here, what do we get? Boom, everything's 0. And that's just e to the 1. Oh, no, this becomes e to the 0, which is what? You guys just know that. Just know anything raised to the 0th power is 1. Do you know why?
Because it's like divided by itself.
Well,
because if you look at it like constant subtraction.
It is divided by itself,
yeah.
yes.
If you
So,
look at it like subtraction.
Yes. So
it would be like e to the 1 minus
x
1 would be like e to
the 0 is the same thing as x to some power p minus itself, right? Which is x to the p multiplied times 1 over x to the p, which is 1. This step is a consequence of the fact that this is the same thing as x to the p times x to the negative p. So anything raised to the 0th power is 1. Because that p can be anything. Next, let's evaluate it over there. So now 1 goes in for my x. And I got 1 times the 0 over here. So this becomes 1 times e to the 0. E to the 0, we just proved any number to the 0th power is equal to 1. But we didn't have to prove it. You guys just knew it. But I wanted to show you why. So that equals 1. So our functions are, their partial derivatives of the function exist. It is continuous at the point 1, 0. So it is differentiable. So let's ask another question here. And I'll delete everything except what's in the boxes because apparently my brain thought it was important. Question number 2. Or more like command number 2. Find the linearization and approximate f of 1.1 comma negative 0.1. So command number 2 is approximate this. Recall a linearization. Some point A, B is equal to our function plus that's a B. So we know what f of xy of AB is because AB, remember, AB is equal to 1, 0. So we know this number right here is a 1. So x minus 1. And plus, we know this number is a what? Oh no, I must have deleted it. Oh, thank you. So we calculated it to equal 1, right? That's when we plug in a 1 for 1, a 1 for x and a 0 for y. So it just becomes 1 times 1, which is 1. Thank you. And then we get y minus our b, which is 0.
Professor,
Yes?
on the equation, is this L of AB or L of XY?
Great question. If I said L of xy, the equation won't work out really well because it already has some x's in it. It already has an x and a y in it. So what I want is I want it to be L of AB, even though I can define an L of xy. I would have to then call this a different variable. So we want to just call it L of AB. Because if I plugged in x over here, then I'd get like x minus x, y minus y. It's not like good math etiquette. We wouldn't get an equation out of it. That's a very good question. You do know these symbols are arbitrary, you know, but although they're arbitrary, they have to be consistent. So AB is just like some concrete point, like 1, 0. And x and y represent any value for the x component and any value for the y component. So, okay. So right now, if we're plugging in these values here, it would be for 0 and 1, or I mean 1 and 0. All right. So over here, this is what my z would be if I plugged in a 1 and a 0. So I put a 1 here. You know, our task was to do it for this, but we're doing it for the original point first. So this is a 1. So notice our equation then becomes, and I'm tired of seeing everything over here. So L of 1, 0 becomes 1 plus x minus 1 plus y. So what is L of this 1.1 minus negative 0.1? It's merely f of 1.1 negative 0.1 plus this function evaluated at these points. X minus my A, which is 1.1. Y minus my B. So a negative minus a negative is a positive. Okay. And you know, yeah, you're gonna have to bust out a calculator to calculate these things. Okay. So what we end up getting is when you plug and chug, it's approximately 0.98. And there you go. You'll most likely be doing this in calculus lab. Or have you already done it? You haven't? Yeah. Yes, totally seems like a calculus lab kind of thing to do. Because you'll get a surface and you'll create approximations for it. You guys did linear approximations for Calc 1 lab, right?
I took Calc 1.
For Calc 1 high school?
Yeah, we did, in our Cal 1 lab, we just like had a group study session.
Oh, okay. Okay. Well, yeah, class is over now. So I got to what I could